Hello. In this short video, we are going to introduce group isomorphisms, and we will see some examples and some non-examples of group isomorphisms. We finish the video by proving Cayley's theorem, which says that every group can be realized as a subgroup of a permutation group. And that would be our source of motivation to study permutation groups further. But what is a group isomorphism? Let's start with looking at Z sub 3, one of the easiest groups that we know. And when I say looking at it, I mean essentially looking at the operation table of Z sub 3. Z sub 3 has only three elements, 0, 1, and 2. To be more precise, I'm talking about the residue classes modulo 3. So I'm talking about residue class of 0 mod 3, residue class of 1 mod 3, and residue class of 2 mod 3. If I look at the addition, the operation on this group, then I get this table. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, and I can continue like this. So there are many observations that we can make out of this. For instance, using the cancellation law, I can see that when I add 1 to these elements, I cannot get repeated elements. So every element should appear exactly once. So 1 appears here, 2 appears here, and then I get 3. And similarly, when I add 2 to 0, I get 2. When I add 2 to 1, I get 0. And when I add 2 to 2, I end up getting 1. Now let's say somebody in the Roman era wanted to write down the same group, the addition table of the same group. They would have used these symbols. Okay, maybe they didn't have 0 at the time, but let's allow them to use O for 0. So we have O, I, and double I. And then the addition table would turn up to be O, I, 2I, and the same for the column. But then I plus I is 2I, and then I plus 2I is 0, is O, and then 2I plus I is O, 2I plus 2I is I. Or if I want to write down this in Persian numbers, so I can write this in Persian numbers. So we know that I'm Persian. I can write this in Persian numbers or Arabic numbers. So they are slightly different. So in Persian, we have this O-shaped kind of 0. In Arabic, it's just a dot. In any case, so we have this. It turns out to be that this is 1, this is 2 in Persian, and I have 0. So then I can write down this table, and it would be the same as this one. Now, here is a question. Am I writing different groups, or are all of them Z sub 3? One can argue that they are not Z sub 3. They are kind of different. So this one has these kind of symbols as elements. But this one has these kind of symbols as elements. And in Persian, I have these symbols for elements. So strictly speaking, as sets, they are not the same sets, and therefore they are not identical groups. But we know from all practical points of view, they are the same groups. I'm just using different symbols. It's enough to have a translator to translate from one language to another to see that they are indeed the same things. So in mathematics, we have many of these translators. What do we mean by a translator? Especially in this abstract sense of mathematics, we can have a very concrete definition for a translator. In practice, in real life, translator is not as clean. But in general, the work of translator is supposed to be something like this, a bijection between these two languages that preserves the property of the elements. Now, in the case of groups, property of elements means that this table of multiplication or addition should go to the other table of multiplication, addition. So we need to have a bijection between the languages. So here, these are the languages that we have. We need to have a bijection. Here the bijection is that I send this one to this, I send this one to this, I send this one to this, and this bijection should send the entire table to this entire table. If we end up getting such a bijection, then at the end of the day, we are working with the same group. I'm just using different language for it. So that's why we will identify these groups, and we say that these groups are isomorphic. Now, let's remember, when we say this table should go to the other table, what does that mean? It means that if I look at this component, this should go to the same thing as over here. But this entry is nothing but this one plus this one. This is mapped to this is mapped to this, and I'm asking that their summation should be added to the summation of these two. That's the definition of being a group homomorphism. So I'm asking to have a group homomorphism from the group with these elements to the group with these elements that preserves, that's also a bijection. That would be our definition of group isomorphism. So let's make it precise. Suppose I give you two groups. One of them comes with operation dot. The other one comes with star as its operation. Now, if I give you a group homomorphism, which is also bijective, then we call it a group isomorphism. And this F plays the role of translate. So it translates, it gives me a bijection for every word in this language. It gives me a word in this language. And it's supposed to be a homomorphism. That means that these words are indeed translation of each other in a sense that they play the same role with respect to the group operation. So that would be the definition of group isomorphism. And if there is a group isomorphism, if there is a translator from G to H, then we say G is isomorphic to H. So from our point of view, if two groups are isomorphic, and we write it like this, if two groups are isomorphic, from a group theory point of view, they should have the same properties. For instance, from the fact that there is a bijection between them, we already know that they have the same cardinality. That we knew from set theory. So if there is a bijection between two sets, they have the same cardinality. But now we have even more information because there is this operation, and this operation in G and H, they look like the same. Using this translator, I can send G to H and preserve this operation. Okay, so here is an important example. Let's say I tell you C sub n is a cyclic group, and its order, its cardinality is n. Remember, we said order of a group is nothing but its cardinality. So let me again emphasize order of a group G is its cardinality. Please do not confuse order of a group by order of an element, even though they are tightly related to each other, but they are different things. We proved in the previous video that order of an element, let's recall this, this is also important, order of an element, if it's finite, the definition of order of an element is the following, that G to some integer power is the neutral element precisely when n divides k. And then we showed that in that case, order of the group generated by G is equal to the order of the element. So you see, even though there is a distinction between order of a group and order of an element, but when my group is cyclic, they turn out to be the same thing. But in general, of course, order of a group is cardinality of that group. Order of an element is this nice phenomena that says that element raised to some integer power is the neutral element precisely when its order divides. Okay, this was a reminder from the previous video. It has nothing to do with this example, but now I want to show this example. Okay, what is the example? The example says that if I tell you C sub n is a cyclic group of order n, then it is isomorphic to Z sub n. So up to isomorphism, there is a unique cyclic group of order n. Up to isomorphism, every two distinct cyclic groups of order n are isomorphic to each other. Okay. Please pay attention. I'm not saying that there is a unique set, there is a unique cyclic group. I'm saying there is a unique cyclic group up to an isomorphism. That means if I give you two cyclic groups of order n, then they are isomorphic to each other. Again, that means there is an isomorphism from the first group to the other one. Okay. Okay, let's see why this is the case. I'm telling you that C sub n is a cyclic group, and I'm telling you that it has order n. When I say it's cyclic, it means it is generated by one element. When I say its order is n, it means its cardinality is n. But remember, I pointed out this, we proved in the previous lecture, in the previous video you've seen, that cardinality of the cyclic group generated by G is equal to the order of the element G. So knowing that cardinality of the cyclic group is n, we can deduce that the order of the element G is n. Now, what does that mean? We said that order of element is n, especially when n is finite. That means G to the k is the neutral element precisely when k is an integer multiple of n. Okay, now have this aside. I'm going to define a function from Z sub n to the cyclic group that we are given. What is this function? This function takes a residue class of k modulo n, and it sends it to this kth power of g. So again, there is this issue of well-definedness. Why is that the case? So this is a big warning. We have to be careful here. So notice that k is a representative of this residue class. So I'm taking the representative and then defining this. In principle, I might have different representatives for the same residue class, but the right-hand side depends on k. We need to justify this. We need to say what happens if I choose another representative. Why do I end up getting the same result on the right-hand side? That we say we need to address the well-definedness of the function f. We need to justify why this is indeed a function. So k is a representative of this, and g to the k depends, g to the k is defined in terms of this representative. I have mentioned this long ago when we discussed equivalent classes and so on. Whenever we choose a representative and then we make a general rule out of it, we have to be cautious about stereotyping. We have to make sure that this representative k, this g to the k, does not depend on this choice of representative out of this equivalent class. Okay, so that's the well-definedness issue. Now let's make it into mathematical formulation. I pick two representatives, K1 and K2. That means I'm assuming the representative, the equivalence class of K1 modulo n is the same as the equivalence class of K2 modulo n. And I need to argue why g to power K1 is the same as g to power K2. As otherwise, this function doesn't make sense, because if these are the same elements, the function is supposed to give me the same output. So I need to argue why I'm getting the same output. Okay, so that's my goal. I start from this equation and I want to get to this equation. But let's try to go one step at a time. What does this equation mean? We know that K1 and K2 have the same equivalence classes precisely when they are related to each other. In this case, equivalence class, equivalence relation means congruent modulo n. So knowing that K1 and K2 have the same equivalence classes modulo n implies, or it's in fact equivalent to saying that K1 is congruent to K2 modulo n. Now, what does that mean? This means the difference of K1 and K2 is an integer multiple of n. And that means K1 is K2 plus an integer multiple of n. So Q is an integer number. Therefore, g raised to power K1, that's what I'm looking for, is, so I'm going to write down K1 as K2 plus n times Q. Then g raised to power K1 is g raised to power K2 times g raised to power nq. Now remember, n is the order of g. That means g to the k is neutral element if k is a divisor of n. Now nq is a divisor of n. nq is a divisor of n. Therefore, g raised to power nq is the neutral element. So it doesn't change g to the k2 when I multiply g to power k2 by g to power nq, because g to power nq is just the neutral element of the element. So altogether, I get that g to power k1 is indeed equal to g to power k2. Okay, so this shows this function that I have defined is indeed a function. So I now have a function from z sub n to the cyclic group c sub n. Next, I want to show that this function is a group homomorphism. That means I have to argue why it preserves it sends the group operation to group operation. So what do I mean by that? When I apply f to sum of two elements, here I'm using dot. I'm writing c sub n in multiplicative form. I'm writing z sub n in an additive form. So I'm going to use f of sum of these elements. By definition, sum of these residue classes is the residue class of some of these integers, and f of this, remember, f of a residue class is nothing but g raised to power that integer. So I need to raise g to power the integer k plus l. Now g to power k plus l is g to power k times g to power l. G to power k, by definition, is f of the residue class of k modulo n. And g to power l is f of the residue class of l modulo n. So all of a sudden we see that f is indeed a group homomorphism, because f of summation is product of f's. So it sends group operations to group operations. It is a group homomorphism. Okay, so far I showed that it's well defined. Then I showed it's a group homomorphism. Now I'm going to argue that it is a bijection. Okay, often it's hard to show that it is surjective. In this case, it's not, but often it's hard to show a function is surjective. It's easier to start with injective. So let's see why it is injective. Okay, so suppose f of the residue class of k is the same as f of residue class of l modulo n. And I need to show that they are the same residue classes. So this is the kind of implication that I want. So I go step by step. By definition, I know that f of this residue class is g to power k. And f of this residue class is g to power l. So I know that g to power k is equal to g to power l. We've seen this technique again and again. Whenever you have this equation, it's better to have neutral element on one side. So we are going to multiply both sides by inverse of g to the l. And inverse of g to the l is g to power negative l. So from this equation, we end up getting that g to power k minus l is the neutral element of g. But now remember, that's the main point of being order of an element. So when we say order of g is n, that means g raised to some integer number, let's call it m, is the neutral element if and only if the order, so maybe I don't even write this. So this happens if and only if order of g divides m. That's the crucial part of definition of order. Of course, this is the case when order of g is finite. Otherwise, it doesn't make sense. So that's the main point of order. G to the m is the neutral element precisely when order of g divides m. Now, if I apply this over here, knowing that g raised to power k minus l is the neutral element, I can deduce that order of g, which is n, divides k minus l. Now, that means k is congruent to l modulo n. And that implies that the residue class of k modulo n is the same as the residue class of l modulo n. Therefore, f is injective. Now, f is injective. F is a function from z sub n to c sub n. Both of these sets have cardinality n, and f is injective. Therefore, f is also surjective. So this is one way of saying it. Of course, in this case, we can also check it directly, because every element of the cyclic group generated by G is of the form G raised to power K, and G to power K is f of the residue class of K modulo n, and therefore every element of the cyclic group generated by G, C sub n, is in the image of f, and so f is surjective. This is a direct way, and here is the indirect way. This indirect way is often used in other situations when it's not that easy to check surjectivity of the function directly. We use the fact that, so hopefully we know that the domain and codomain have the same cardinality, and if they are finite, then it would be enough to show the function is injective in order to deduce that it is surjective. Okay, altogether now we showed that this function f is a bijective group homomorphism. Therefore, it is an isomorphism, which implies that every cyclic group of order n is isomorphic to z sub n. So this gives us a kind of classification or understanding of cyclic groups of order n up to isomorphism. Next, we are going to discuss that positive real numbers under multiplication is isomorphic to the entire real numbers under addition. So I'm changing the operation. Here it's multiplication, here is addition, but I'm also changing the set. Here is the set of positive real numbers, and here is the set of real numbers. And I want to say that they are isomorphic to each other as groups. We know that the set of positive numbers under multiplication forms a group, and the set of real numbers under addition forms a group. Now, what is the isomorphism from here to here? We've seen an example of a group homomorphism from our positive reals to reals. And luckily, that's in fact a bijective group homomorphism, and therefore it's an isomorphism. Let's recall what the group homomorphism was. It's already here, and you've seen it. It's the natural logarithm. Of course, there are other homomorphism as well, but let's stick to this natural logarithm. So the natural logarithm map from positive real numbers to real numbers is a well-defined function, and we've checked that it is a group homomorphism. It sends it's a group homomorphism because natural log of xy is the natural log of x plus natural log of y. You've seen this in calculus. And therefore, it's a group homomorphism. And natural log is a bijective map because it has an inverse. If I look at the exponential map from real numbers to positive real numbers, which sends x to e to power x, is e the Euler number, e to the x, then this is the inverse of the natural log. And therefore, natural log is a bijection from positive real numbers to real numbers. Altogether, we deduce that natural log from positive real numbers to real numbers is an isomorphism, where here I'm looking at this one under multiplication and this one under addition. Now let's see some not examples, in a sense that let's see how we can show two groups are not isomorphic. Okay, for instance, the group of rational numbers under addition is not isomorphic to group of integers under addition. Okay, let's see how we can prove this. Suppose to the contrary that it is. Suppose that there is an isomorphism from Q, let's call this isomorphism F, which goes from Q to Z. I want to reach to a contradiction. Notice that F is a bijective map, and therefore, in particular, it is surjective. So there is something that's mapped to a generator of Z, and we know that Z is generated by 1. So there is some rational number that is mapped to 1. So there is some rational number m over n which is mapped to 1. Now I'm going to look at half of 1. So that's my goal. But there is no half in Z. That's the whole point. But there is a half in Q. That's what I want to get to. So m over n can be written as m over 2n plus m over 2n. That we can do in rational numbers. So 1 is f of m over n, and that is f of m over 2n plus m over 2n. But f is a group homomorphism. So it preserves addition, meaning f of summation is summation of f's. So I can apply f to the first one and then add as we apply f to the next one. But now notice, f is a function from Q to Z. So f of m over 2n is inside Z. All of a sudden, I'm writing 1 as an integer multiple of 2 because I'm adding this guy to itself. I'm getting twice this integer. This is a contradiction because this side is odd and this side is even. So we get a contradiction, and therefore there is no isomorphism between Q and Z. Now, you can ask, how did I think about halving this kind of thing? So why did I do that? The general rule of thumb is the following, that if two groups are isomorphic, then they should have the same set of equations, so to speak. So in a sense that because I have a solution for 2x equals to 1 in one of these groups, I need to have a solution for this equation in the other one as well. And that was the source of contradiction for us. Okay, this is a a bit of a cheating version of this solution. But it is always good to think about equations when we are dealing with isomorphism of groups, especially when we want to say two groups are not isomorphic. Using this idea, we go to the next example. We want to show that non-zero complex numbers under multiplication are not isomorphic. This group is not isomorphic to non-zero real numbers under multiplication. So again, suppose to the contrary that there is an isomorphism, and I want to think about an equation in here that's not satisfied in this one. Immediately, we can think about something like x squared equals to -1. Okay, but what is -1? Can I detect -1 in terms of multiplication? -1 is a number whose square is 1. So I'm essentially thinking about a solution for x to power 4 equals to 1. X equals to 4 equals to 1 has 4 solutions here, but it has only 2 solutions here. So that might help us to show that these guys are not isomorphic. Okay, of course, this is one way of doing it. There are many other ways of doing it. For instance, here there is only one bounded order element, but here we have many. So if I tell you x to the n is 1 in non-negative, non-zero real numbers, x to the n equals to 1 implies that x is either +1 or -1. But in complex numbers, of course, it has n solutions. Again, the underlying technique is looking at equations. But here I'm going to look at the concrete example of x to the power 4 equals to 1. Okay, but let's make it concrete, see how we can proceed. So suppose to the contrary that f is an isomorphism from non-zero complex numbers to non-zero real numbers, then the neutral element of this guy is supposed to be sent to the neutral element of this guy. And therefore, f of 1 is 1. Okay, so 1 is the neutral element here, 1 is the neutral element here. Every group homomorphism sends neutral element of the domain to the neutral element of the codomain. So f of 1 is 1. Now, f of I to power, okay, f of -1 squared is f of, I can bring negative squared inside because f is a group homomorphism. And that is f of 1, and f of 1 is 1. So f of -1 squared is supposed to be 1. And it's a real number. The only real number whose square is 1 is either 1 or -1. So f of -1 is either 1 or -1. But remember, f is a bijective map, is bijection, and f of 1 is 1. So f of -1 cannot be 1. So it's bijective. F of 1 is 1. So f of -1 cannot be 1. It's not -1. It's not 1. But it is either 1 or -1, so it should be -1. So f of -1 is -1. Okay. F of I squared is f of I squared, and that one is f of -1, which is -1, and that gives us a contradiction because f of I is supposed to be a non-zero real number. And now there is no non-zero real number whose square is -1 because every real number squared is always non-negative. So it cannot be -1, and that gives us a contradiction. Square of a real number is always non-negative, and we get a contradiction out of this. Of course, as I've mentioned, we could have also argued, after we showed that f of 1 is 1, we deduced that f of I raised to power 4 is 1, f of -I to power 4 is 1, f of ±1 raised to power 4 is 1. We get all of these equations, but x to power 4 equals to 1 has only 2 solutions. In non-zero real numbers, in real numbers. So from here, we deduce that we cannot have 4 distinct elements in real numbers that are zeros and that are that are solutions of x to the 4 equals to 1. That means that f cannot be a bijective map because either f of I is equal to f of -I. So all of these f's cannot be distinct. Therefore, f cannot be bijective. From there, we get that's another way of getting a contradiction. In any case, now we've seen that we've seen some examples where some non-examples. So when we saw some techniques of showing two groups are not isomorphic. Now, next we are going to show Cayley's theorem. Cayley showed that every group, every abstract group, can be viewed as a subgroup of a symmetric group. So using his method, we can also show that if I start with a finite group, I can view it as a subgroup of a symmetric group on finitely many, on a finite set. And therefore, every finite group can be viewed as a permutation group. So a subgroup of a symmetric group is called a permutation group. So that way, Cayley said that these abstract groups can be realized as concrete groups, concrete subgroups, these permutation groups. Even though from classification point of view, this Cayley's result is not completely satisfactory, but it is interesting to know that even though we have started with these abstract formulation of groups, at the end we are working with permutations. Okay, so let's see the precise formulation of this. Here is Cayley's theorem. So suppose that G is a group, then G is isomorphic to a subgroup of the symmetric group on the same set. So this means S sub G is the set of all the bijections from the set G to the set G, and I'm thinking about it under composition map. So every finite group, as a particular case of this, every finite group can be realized as a subgroup of a finite symmetric group, because this cardinality of G would be finite. So here I give you a group G. I want to realize this as a subgroup of a symmetric group. The key point is what I've mentioned earlier when I was talking about the multiplication table. I said that, okay, let's order the elements of G over here. And when I give you an element of G and start multiplying them, G times E1, G times G1, and I continue like this, I said that what happened? I said that because, let's make sure that everyone are on the same page. Okay, that's good. We said that because of the cancellation law in a row, we cannot have repeated elements. You see, if G times two of these things are equal, then I can cancel out G. Then those two things should be equal. So because of the cancellation, in every row, there is no repetition. In fact, in every row, every element appears as well. If it is finite, we immediately get it because of the fact that the map is injective and they have the same cardinality. We deduce that it is also surjective. And from there, we get that in every row, we have permutation. This is the key idea behind Cayley's theorem. So now let's go into the details of the argument. And let me remove this. So as I pointed out, I'm looking at the row corresponding to G in the multiplication table, and that means I'm looking at multiplication by G, left multiplication by G. This L kind of stands for left. So I'm looking at left multiplication by G, and that gives me a function from G from the group to itself. When I feed it an element of the group, it gives me G times that element. Now, I'm going to show that this is a bijection, and therefore this is an element of S sub G. Later, we are going to use this in order to get a function from G to S sub G. Okay, so but bear with me. First, let's look at L sub G and try to show that L sub G is a bijection, and therefore L sub G is an element of the symmetric group of the set G. In order to show that it's a bijection, it is enough to show that it's an invertible function. So I'm going to produce an inverse for this function. And magically, the inverse is nothing but left multiplication by G inverse of the element. When I do the computation, the magic goes out, hopefully, especially when we discuss the homomorphism later. So let's see what is the composite of left multiplication by G inverse and then left multiplication by G. So I'm looking at this composite. I feed it an element of the group, X. The first one says I need to multiply X from left by G inverse. The next one tells me that I need to multiply this product by G from left. Now I can use associativity, reorder the parentheses, and cancel out G by G inverse. I end up getting X, which means that this composite, when I give it X, it gives me back X. So that means this composite is the identity function. Similarly, when I apply left multiplication by inverse, G inverse, to the left multiplication by G, and then I feed it X, what do I get? I get, again, left multiplication by G is G dot X. Then I need to multiply further by G inverse. So I get G inverse dot G dot X. And again, by associativity, these guys disappear. I end up getting X. So composite of these two functions from both sides give me the identity. And that means that these functions are inverse of each other. And therefore, both of them are invertible. Both of them are bijections. In particular, we get that L sub G is a bijection. So that tells me that L sub G does belong to S sub G. Now I am ready to get a function L from G to S sub G. This function is nothing special. When I feed it an element, it gives me this bijection that we have produced. We know that L sub G is a bijection from the set G to itself. Now I give it G, it gives me this bijection. My claim is that this function L is a group homomorphism. Okay, so it can be confusing. The trick is try to understand each one of these functions, what is the domain, what is the codomain, and think about what we want to show one step at a time. So if you want to think all of them at the same time, then it might get more confusing. So try to understand each one of these functions one step at a time. So L is a function from G to S sub G. What is S sub G? S sub G itself consists of bijections. The way that we are defining it, L parentheses G is supposed to be L sub G. Okay. One trick is to work with the symbols, and then each time symbolically ask yourself, what am I supposed to do with these symbols? And then when you reach to a certain equation, try to show that equation by asking yourself what it means from each side, on each side of this equation. For instance, I want to show that this is a group homomorphism. What does that mean? Forget about the meaning of L, what it is, and so on, but rather symbolically. If I tell you L is a group homomorphism, what does that mean? It means when I give it a pair of elements of the domain, then L of G1 dot G2 is supposed to be the product of L's. So I need to apply L to the first one and L to the second one. But the product is supposed to be operation of the codomain. And operation of the codomain is the composite. So I need to look at the composite of this and that. This is the equation that I'm looking for. Now, it looks complicated. What does that mean? This is an element of S sub G. These are elements of S sub G as well. Elements of S sub G are functions from G to G. This one is L sub G1 dot G2. This one, L sub G1, small circle, L sub G2. I want to show the equality of these two functions. Both of them are functions from the set G to the set G. When we want to show equality of two functions, first we need to check if they have the same domain and codomain, and in this case they have. Both of them have G as their domain and codomain. So it's enough to see whether or not they have the same rule. And that means I need to check that for every x in the domain, what I get from the first function is the same with the thing that I get from the second function. So this is my goal. I want to show that what this function gives me at x is the same as what this function gives me at x. Okay, now let's start with the left-hand side. What is this? This tells me that I need to left multiply this element by x. That is how we define L parentheses G. L parentheses G at x is G, left multiplication of G by x. So again, let me write it down. For every G, L parentheses G of x is L sub G of x, and that is G dot x. So left multiplication of G by x. So L of this element at x means this element times x from left. So this element times x from left. Now let's look at the right-hand side. The right-hand side is composite of these two. This means I need to compute L of G1 at this element. Now, what is the guy inside? The guy inside is G2 dot x. And then when I want to compute this, I need to further multiply by G1 from left. I have written this over here, so let's go over that. So the guy inside is G2 dot x, and this means that from left I need to multiply I need to multiply G1 by this. So I get G1 dot G2 dot x. Now, question is whether or not this is equal to this one, which is the case because of associativity. By associativity, I do have that this product is equal to G1 dot G2 dot x, and that means that L of G1 dot G2 is the equal to L of G1 O L of G2. Therefore, this equality holds for every x, and that means that L of G1 dot G2 is equal to L of G1 O L of G2. If you think about it, this is what we have actually done in the when we wanted to show injectivity, bijectivity. So here we argued that L of G composed with L of G inverse is identity. Now, if you think about the line of argument that we had, this is precisely the same thing, because it's the same as L of the neutral element, and multiplication by a neutral element doesn't change anything, and that is the identity now. So that was hidden in the way that we proved bijectivity of L sub G. Okay, now we have proved that L sub G is an element of the symmetric group. Then we use this to define this function L from the group G to the symmetric group G. We showed that this function L is a group homomorphism. Next, I want to show that it is injective. Okay, let's see why it is injective. Injective means what? Injective means that if I tell you L of G1 is the same as L of G2, I need to argue why G1 is equal to G2. So I need to show that this implies question mark. Why does this imply that G1 is G2? That means injectivity. Okay, when I tell you that L of G1 equals to L of G2, what is L of G1? L of G1 is nothing but this bijective map. So it is left multiplication by G1 gives me the same function as left multiplication by G2. In particular, when I feed the neutral element to both of these functions, I end up getting the same elements of the group. But remember, this means multiplying from left G1 by this element. That means G1. From left, I need to multiply G2 by the neutral element. Then I get G2. So this equality implies that G1 is equal to G2. And that's exactly what we wanted to show. Therefore, L is an injective group homomorphism from G to S sub G. Now, if I focus on the image, we know that image is a subgroup of the codomain. That we proved long ago. So image is a subgroup of the codomain. Then L would be a bijective map from G to the image of L, because L is injective. If I restrict my codomain to the image of L, then L would be surjective, and therefore we end up getting a bijective map from G to image of L. So let me repeat this. So if I think about L as a function not from G to S sub G, but rather from G to the image of L. Image of L is a subgroup of S sub G. Now we showed that this is a group homomorphism. We showed that it is injective, because L is injective. By changing the codomain, I ensured that it is surjective. So it is injective, it is surjective, therefore it's bijection. It's a bijective group homomorphism, and so it's an isomorphism. That means that G is isomorphic to this subgroup of the permutation groups. That's exactly what we wanted to show, and that is Cayley's theorem. Now, because of this, Cayley's theorem, we get motivated to study symmetric groups in more details, and that's what we are going to do next.